Hi, welcome to part 2 of the integral test. Today we're going to discuss the remainder of the integral test. What the remainder does is it tells that it gives us a range at which the sum of a series can converge to, provided the series does converge. Now you may recall yesterday we took the summation of 1 over n squared plus 1, and using the integral test we discovered that because the integral converged, that the series converged by the integral test. Well, we found out the integral, it converged to pi over 4. But remember, that is not what the series converges to. The problem is, we don't know what this series will converge to. But using what we call the remainder of the integral test, we can get a pretty accurate range to determine between which two values the series will converge to. We call this the remainder. Now, what is the remainder? Well, it's very simple. R sub n. This is the remainder of the nth term. Now, to get the remainder, we take the actual sum minus the sum of the first n terms. And that's really what this is. This is the actual sum. Now, this is an unknown sum. We don't know what that is. But S sub n, we can get that. That is the sum of the first n terms in a sequence. And we can get that. That's just a summation right there. Now, what this is going to give us is it's going to give us a range. And we'll talk about that in just a moment here. So, if we go down here to this example, we have this convergent series. Now it has to converge. Now this time they tell us. If it doesn't tell us, we have to determine it does. It wants us to approximate the sum of a convergent series by using the first 6 terms. Well, that's easy to do. We're just going to use our calculator for that. Remember the sum of the first 6 terms. We let n be 1. We get 1 over 1 to the 4th plus 1 over 2 to the 4th plus 1 over 3 to the 4th, all the way up to 1 over 6 to the 4th. And I'm just going to use the calculator to go ahead and get that value right here. Give me a second here. Dot B, always clear it out. And we may remember how to do this. We're going to take the sum of a sequence. And let me see here, control divide, that makes me my little fraction. I'm going to go 1 over, whoops, delete, 1 over x to the 4th. I like to use x, I think you can use n. And comma, x, comma, 1, comma, 6. Now what I'm going to do to make sure it gives me as a decimal, up here on the 1, I'm going to put a decimal there. And that's going to make sure that my answer comes out as a decimal. And so I get this 1.0811. Well, this is the sum of the first 6 terms. Right there. Now, what we're looking for next, we want to include an estimate for the maximum error of our approximation. Well, to get the maximum error, we just want to find out just how far off we can be. Well, to get that, it's a little bit. I want to find the error or the remainder of our series right here. Well, to get the remainder, right, I'm going to take what my actual sum is minus the sum of my first 6 terms. And what we wind up with is the following. We wind up with S minus 1.0811. Now, this number right here will give me the remainder. It'll tell me what my error is going to be in my approximation. If I take the actual sum minus the sum of my first 6 terms, that's going to give me what my error is, how far off I am from the actual value. Now, we can use this to get a range of possible summations to the infinite terms. We do this by looking up here. Now, the remainder or the error is going to be somewhere between 0. Now, why 0? Well, if we're spot on, get the actual sum, there's going to be no error. Between 0 and this integral. Now, this integral right here is basically telling me it's the sum of all the other terms, of the terms from 6 to infinity. So this is going to give me the summation. This is going to give me the sum of all the other terms beyond 6. Now, why would we want that? Well, this is gonna add up all the other ones. So I can use that down here. I know that r sub 6, my remainder, has to be between 6 and from 6 to infinity of f of x. We're just going to convert that to f of x, 1 over x to the 4th dx. So, whoop, that's a 0 there, sorry. So what they're saying is my remainder has to be somewhere between, my error has to be somewhere between 0 and the sum of all the other terms here. In other words, my difference between my actual values, my actual and my approximate value, has to be between 0 and the sum of all the rest. Basically, if I add this 1.0811 to all the terms after the 6 terms, that's going to give me my maximum error here. And that's what I'm kind of looking for right here. So what we have to do is we have to calculate this. And unfortunately, we've got to do a little bit of math there. So we're going to take a limit, because it is an improper integral, as b goes to infinity, of 6 to b. Why do I use 6 and b's? Why? And this is just going to become x to the negative 4 dx. If we integrate it, we get the limit as b goes to infinity of from 6 to b of negative 1 over 3x cubed. And just simplifying that out a little bit, we get the limit as b goes to infinity of negative 1 over 3b cubed plus 1 over 3 times 6 cubed. Okay, well, I don't know what that is, but I know that goes to 0, but that's why we have a calculator. Okay, so I turn on my calculator. I'm going to go 3 times 6 cubed, 3 times 6 to the 3rd, and that gives me 648, 1 over 648. And I divide that. So I'm going to, let's see here, 1 divided by 648, put a decimal there, hit enter, and it gives me 0.0015, and on and on and on and on, forever. Okay? So what this is the maximum possible sum of all my other terms. See, this is the sum of my first 6. I would be adding at most 0.015432 blah 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 to get the rest of them to infinity. So that's going to give me kind of like my maximum possible error there. What's the most I can add? And then I can rewrite this. S minus 1.0811 between 0 and my maximum possible sum, and I add. Therefore, I add it to both sides. My actual sum has to be between, add it to both sides, 1.0811 dot dot dot, and let me see if I add it to the other side, what do we get? Let me see. I'm going to take 0.0015 plus 1.0811. Hit enter, and I get 1.0826 dot dot dot. So what we're saying is that the actual sum has to be between 1.0811 and 1.0826. And that's going to be pretty accurate. And we do this all the time for numbers, like even pi, for instance. We know pi is between 3.14 and 3.15. We know it's going to converge, but we don't know what it converges to. But we can say safely it's going to converge between these two numbers. Same thing here. I know the sum is going to converge. It's going to approach a specific number. But we don't know what, but we can say it's going to converge between 1.0811 and 1.0826. So very useful for us to do it in a lot of mathematics. Okay? Alright. I hope you guys had fun. I'll see you later. Bye-bye.